What's a programming language? Well, a programming language provides tools which simulate how humans solve problems. So memory, asking questions, repetition. What's an algorithm? An unambiguous set of instructions for solving a problem.
Yes.
Fair enough?
There you go.
Kind of like a recipe. Okay, so a set of unambiguous, how do you spell this? US instructions for solving a problem.
A detail.
Whatever. You like that? You like detailed?
Yeah.
A detailed
There we go.
set of instructions, set of unambiguous instructions for solving a problem. Kind of like a recipe. So, I said that programming languages have to provide us with equivalences to these three things. How do we handle memory? How do we handle asking questions? How do we handle repetition? Programming languages provide us memory through something called variables. They provide us a simulation, the ability to simulate asking questions through something called conditionals. Maybe you say if statements. And repetition through loops. It doesn't matter what programming language you're using. It gives you tools that simulate these three things. Okay? Whether it's Visual Basic, Java, PHP, C#, Forth, really old language. Doesn't matter. All programming languages are the same. The only thing that's different is the syntax. They're all trying to accomplish the same thing. But now we need to talk about languages in general. Languages. There are three types of programming languages. We have high-level languages. We have low-level languages. And we have and machine language. All right, machine language. Zeros and ones. So how many of you have the little 2-key keyboard at home? Get out, do your Visual Basic programming, just pop out the 2-key keyboard, just keep hammering it out.
Thanks. Yes.
0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0. Why not? We would drive ourselves insane.
And we have to interpret that in regular.
Now, there's no interpretation there. We're talking right to the machine.
No, I mean for us, humans mentally, they have to put it into, just break it down.
Okay.
From English.
Instead
to
of instead of using tools that allow us to do what's easy for us and have that translated into what's easy for the computer, we're going to just talk directly to the computer. We're going to go down to the computer's level and just talk zeros and ones.
Which is doing too much.
Why should we be inconvenienced? Right? That's the computer's problem. All right. Low-level languages have a one-to-one relationship with the CPU. And let me do this other one, then we'll talk about that for a second. High-level languages have a one-to-many relationship with the CPU. What's a CPU? How would you know a CPU in the wild if you saw one?
Uses hardware resources like.
Well, no, I mean you're walking down the street and there's a CPU laying on the sidewalk. How do you know it's a CPU? What does it look like?
Small cell.
Little square chip thing, right? Okay? With a bunch of probably little metal rods coming out of the bottom of it. Right? That's what a CPU looks like. Okay, so we saw one of these dudes climbing around in the grass. All right, now, how does the CPU accomplish its goal? You said its goal is to communicate with the hardware, to communicate with the software, to act as the central brain, to do all the thinking, blah, 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 right? How does it accomplish that?
It has memory.
It does have memory. I agree. It doesn't tell me how it accomplishes it.
Translate 0 and 1s into high volume and low volume.
Takes the programming language.
I
to
like
zero.
this idea of translates. A CPU knows how to do a bunch of magic tricks. Okay? So we take our Intel processor that's sitting inside of one of your computers, let's say the Intel i7 processor, which is one of their latest, greatest chips, blah, blah, blah. It has a big, long list of things that it knows how to do. Okay? Now, from our perspective, each of those things doesn't seem like it's doing all that much. Maybe one of the things it can do is move a piece of data from this place to this place, and we're supposed to be impressed. Maybe another thing that it does is it takes something that's in this place and copies it into something that's really fast, some piece of memory over here. So it's all these little tiny granular magic tricks that the CPU knows how to do. Big old list of them. Okay? Now, each of those magic tricks represents part of solving a problem. And if you call enough of those magic tricks in a row, in the correct order, a problem gets solved. All hard problems are made up of a bunch of easy parts. So pick the most complicated software you've ever used, whether it's Microsoft Windows or Photoshop or Illustrator or some video game, whatever it is. Okay, it doesn't matter what that program is. I guarantee if you were to look at the source code, you're going to see the same crap we're going to write in here in a beginning programming class. You're just going to see a lot of it. Okay, instead of it being a program with 50 lines of code in it or 60 lines of code in it, you're going to have a program with thousands and thousands and thousands of lines of code in it. So all hard problems, all complicated programs are made up of a bunch of easy parts. Just like our CPU has a whole bunch of little tiny granular magic tricks, granular things it knows how to do. And ultimately, we tell our CPU how to solve problems by saying, do magic trick 1, followed by magic trick 8, followed by magic trick 17, followed by magic trick 3. Poof, problem solved. Okay? That's what a CPU does. Okay? Now he said something about zeros and ones. A CPU translates low-level languages into zeros and ones. So it's a translator. At the end of the day, we're feeding a low-level language to the CPU. And the CPU looks at each instruction of a low-level language, which, by the way, remember, low-level languages have a one-to-one relationship with the CPU. So every instruction of a low-level language equates to exactly one, I call the magic trick. One magic trick that the CPU knows how to do. Okay? But now, the CPU is going to take that low-level language, that instruction, and it's going to map it to some machine code that represents a magic trick that it knows how to do. So inside this CPU, the CPU we see when you go to newegg.com and you buy a processor, it's a nice little chip, and you can see all the little prongs on the bottom of it. Then it has kind of a metal topping that helps dissipate heat. Then it comes with a giant fan to help dissipate heat even more, right? You have all these parts, but the actual processor, you're seeing the finished product. You're seeing a printed circuit board. But before that, somebody had to invent that processor. What do? Well, they had all these wires, and each one of those little magic tricks was actually solved. It's like a little miniature program written in hardware. So somebody had this wire going here, and this wire going here, and this wire going here. So when you put electricity in here, it flows through these wires, and this is what comes out. So if you pass in a 0 and a 1, what comes out is a 1, for example. And that 1 represents the solution to some problem. Okay, so somebody had to solve all those problems by hooking a bunch of wires together and using soldering irons and things like that. And ultimately, after they had it solved, they created the final chip that has all that stuff integrated. Now, so our processor has a whole bunch of mini programs solved on it in hardware. And each one of those solutions, each one of those working algorithms has a code associated with it. And each low-level instruction, each low-level programming language instruction translates to exactly one of those codes. That make sense? Okay. So, low-level languages, one-to-one relationship with the CPU. Now, high-level languages, these are languages that have a one-to-many relationship. Every line of code, that we write in a high-level language may translate into many lines of code in a low-level language, which then translates into many lines of code, many calls to magic tricks on the CPU. Make sense? Human beings kind of like these guys. We like power tools, right? We like to write less and see more. All right. So, 3 types of programming languages. We have high-level languages, we have low-level languages, and we have machine languages. Here are 3 types of programming languages. Didn't we just write that? We have functional languages. We have procedural languages. And we have object-oriented languages. Each of these slides deals with programming languages from a different angle. Okay, so this one, there's 3 types of programming languages from the angle of how the instructions in those languages relate to instructions on the CPU. That's what this first one's talking about. Okay. This next one's talking about 3 different types of programming languages from the perspective of conceptually how do we solve problems using these languages. All right. Functional languages are a little bit weird. I'm just going to kind of gloss over it like super quick. Functional languages use functions to solve problems. I'll swing back to functional languages here in a little bit when I have a little bit something else to base it off of. Okay? Functional languages are not going to be important to us in here. All right? But I'll give you a little more explanation on that. But these other 2 are important. Procedural languages tend to be linear in nature and are monolithic and have a monolithic main. That'll make more sense too as we talk more about this stuff. Procedural languages tend to be our little bit older programming languages. So some examples of procedural languages might be C, Pascal, COBOL. Okay? These are older languages, not necessarily bad languages, but older languages that do, I would say, a less realistic job of simulating how human beings solve problems. Okay, so think when a human being solves a problem with a procedural language, we just basically feed it an instruction after an instruction after an instruction. Do this, then do this, then do this, then do this, over and over and over again, giving us this linear nature to our program and just a big old monolithic main. And what I mean by monolithic main is in a little bit, I'll say something to the effect that all programs begin and end with main. We have this thing called a main method. And when you run your program, it starts at the top of main and keeps going to the bottom of main. And it might take some twists and turns somewhere in the middle. Okay? But procedural languages tend to produce very monolithic mains. Monolithic meaning huge and scary. Okay? Technical term.
Very Webster-like.
So, object-oriented languages represent the way human beings solve problems much more precisely. These are much newer languages. These guys encapsulate detail inside of objects. And we solve problems using the public interfaces. Now, of course, having a PhD, I love explaining easy concepts in a complex way. So now let's take this down and let's talk about it like human beings understand. Procedural languages. So let's say that we have a telephone laying here on top of this table. All right? Now you walk in the door, and I tell everybody, identify what's on this desk. Take out a piece of paper, put your name on it, blah, blah, blah. But what you see up here is a big old pile of wires. Just a big stack of wires, and as you're kind of digging through it, you see, oh, there's a handset somewhere, and you got kind of the dialing button somewhere in there. But to you, at a glance, it's a pile of wires. Can a pile of wires be a telephone? What's a telephone? Something you can make phone calls on, right? Could I have a pile of wires there that technically could make a phone call? Sure. They're all hooked up in the right way. Doesn't look good, but you could still make a phone call with it. I could have the procedural version of a telephone sitting on here, where you see all the details, everything, all the inner workings. But when you actually use a telephone, do you need all those details? No, you need the buttons and the handset. That's it. So, as consumers, as the users of those devices, we solve problems with our cell phone all the time, right? How many of you used your cell phone today? And most of us probably didn't even use it to make a phone call. We checked our email, or we sent a text, or we did all these other things that these phones do today, right? Okay? As a user of it, we don't care about the details as long as it works. We care about the public interfaces. We care about the features that it exposes to us so that we can accomplish what we're trying to accomplish. We don't want to see the chips and crap. That make sense? Yeah. Procedural languages show us the chips and crap as well as the public interfaces. Object-oriented languages just show us the public interfaces. They wrap all the details, which we know are there. Look, we'll take your word for it. Put it in a nice plastic case, or if you're Apple, put it in a glass case and charge us 3.5 times for it. Okay? But hide it from us. We don't want to see it. Make sense? So object-oriented languages are a more modern approach to problem solving because they allow us to solve problems in a way that's more like human beings solve problems. Now I want to emphasize here that the object-oriented version of a telephone, like we're using here in our example, does not have less detail. Just once we've written that detail, we hide it from the user, the person who's going to use that object. And sometimes objects are defined in terms of other objects. So inside of that telephone, aren't there probably other objects that are built with their own detail that then have public interfaces? And maybe inside of that guy, there's other objects that have their own detail with public interfaces, so on and so forth, all the way down to a very, very small microscopic level. Okay? So the way human beings solve problems is in terms of those public interfaces to real objects. Whether we're building something out of Legos, whether we're building a house, whatever it is. We use a whole bunch of different types of objects, a whole bunch of different types of tools, and we put them all together to solve a problem. You're mowing your yard? Well, you have a lawnmower. A lawnmower has internal parts. You didn't build it. You just know that you put gasoline in it, and you pull the ripcord. You can push it around your yard and your grass gets shorter. Then maybe you have the leaf blower thing, right? You go around and blow the leaves off. That's another tool. Inside that, there's a motor. What's the motor have? A motor has rotors and all these other things. It has all these parts that we don't have to understand in order to use it. Right? Okay, so procedural, we see all the details. Object-oriented, we only see the stuff that's important. Make sense? And if we had to get to the details, we can. Somebody had to write the details. There are two types of programming languages. General purpose and domain specific. So these are the different kinds of programming languages there are in terms of the types of problems they were designed to solve. General purpose languages are languages specifically designed for solving a broad classification of problems. General purpose problems. So general purpose programming languages tend to be very large, tend to have lots of moving parts, lots of built-in tools, because the types of problems that they're designed to solve are literally infinite. Okay? General purpose, domain specific. Okay, so domain specific languages are languages designed to solve a very specific type of problem. Good example of domain specific language would be HTML. That's an excellent example of a domain specific language. So HTML, hypertext markup language, is the web page language. What's its job? Its job is to allow you to describe content in such a way that it looks pretty in a web page, in a web browser. That's it. You're not writing loops, you're not remembering stuff, you're not calculating the factorial of a number. All you're doing is making stuff look pretty. So the size of HTML is like this compared to the size of Java, which is the size of a mountain, relatively speaking. Okay? Because Java has to accomplish a lot more. If you'd allow me real quick, because it just popped in my head, some examples of object-oriented languages. Java, C#, Objective-C. From my perspective, these are our big three today. For modern day, high-level object-oriented languages, there's a couple other things I haven't taught you about yet, so I can't say them yet, are going to be Java, C#, and Objective-C. Okay? And really, if we had talked about 6 years ago, we probably would have left Objective-C off. Objective-C is the Mac language. And the reason it's popular today is iPhone. So historically, I mean, you have, I'm going to round down and say, a zillion Java programmers and a zillion C# programmers. And historically, you would have had like 5 Objective-C programmers. Okay, but now you probably have several 100,000 Objective-C programmers because of how popular writing iPhone apps has become. And now that's translated into writing Mac apps. Is writing apps for the iPhone versus writing apps for the Mac kind of the same diff. Okay? There we go. Okay. So a good example of domain-specific languages would be HTML. That's probably your best example. Very tiny language that solves a very small problem. Okay, somebody can learn HTML in a weekend. All right? General purpose, we could fill in our big 3 right there. Java, C#, and Objective-C. We have 2 types of programming languages. We have strongly typed and loosely typed languages. So now, this slide talks about the different types of languages as it relates to the types of variables, or how the variable system works, how they simulate memory. Strongly typed languages require that when you're creating a variable, when you're creating a place in memory to store a value, you must say what kind of value, what type of value that you intend to hold. A loosely typed language doesn't require you to tell it what kind of value you're going to store in there. Okay, so the difference between a strongly typed and a loosely typed language is just that. How much you tell the language about what you intend to store in your variables. Now, I know I told you no trick questions, but I'm going to ask you a trick question. Which is better?
Loosely.
Why? Oh, I love it. You got two different answers. Okay, loosely. Why is loosely better?
Because you can use like any number of ways. Like it's not specific to one use.
Okay. Because from a human being perspective, it's stupid to go to Target, buy a perfectly good container, use it for one thing, and as soon as you don't want to store that in there, and then you come across some other crap like old wires or something you want to store, to have to run back to Target to buy a new container all over some Post-it note. Right? We don't want to have to do that. It seems stupid. Okay? What's bad about loosely typed languages? See, now this is where that gray area starts coming in. From a human being perspective, well, first I'll make the blanket statement. Very often, the human version of right or the human version of fairness does not translate equally to computers. Okay, computers operate on a whole different time level than people do because of how quickly they are. You know, when I teach the operating systems class and we talk about processor scheduling, you know, human beings, if you go to McDonald's and you get in line, there's a version of fair for human beings, right? Who's in front of the line? The person who got there before you. Human beings' version of lines are first come, first serve, right? Not for computers. Some things are more important than other things. We let them go to the front of the line. What happens if you're at McDonald's and somebody tries to cut in line? Everything's relative to how hungry you are. So the version of fairness for human beings doesn't always translate into computers. So clearly from a human being perspective, a loosely typed language makes more sense. We want to be able to repurpose that bucket. From a computer perspective though, from a programming language perspective, a loosely typed language actually has some performance problems. Because before you can use, remember we're talking about variables here. Before we can use the value stored in a variable, we need to know what kind of value it is. For instance, you don't want to be doing math with things that are not mathable. I made that word up. PhD counts. Okay? Can't do math with things that are not mathable. That makes sense. So in a loosely typed language, somebody's going to have to check to make sure the value is mathable before it allows you to do math with it. Strongly typed language, the programmer actually said what's in this bucket, what's in this container. Okay? We were explicit about it. We said, there be integers in here. So go ahead and math away. That make sense? Okay? Now, even having said that, you still can't necessarily answer the question of which is better, strongly typed versus loosely typed. Because it really depends. Not all programs need to be high performance. Okay, but performance does come into play here. Most of the time when we're using our computers, we're nowhere near maxing out our chips. Most studies show that your computer sits idle between 97 and 99% of the time. So those of you who get these gaming rigs with dual 6-core processors, we have 12 cores, and they're all hyper-threaded, so it's actually a 24 logical core. We got 32 gigs of RAM, and you know what I did? I overclocked it. So what I did is I dipped the entire machine into a bucket of ether. That's coolant. Okay, so you got this awesome, amazing machine, and what are you doing? You're checking your email. You know, Minnesota Slim here can check his email just as fast as you can with that thing, that behemoth that's sitting in ether. Okay, so punchline here is that computers operate on a whole different level. We only need that kind of horsepower when we need that kind of horsepower. Where you'd really see a difference is, let's say we had a big video. Let's say you took today's lecture and you decided you wanted to convert it to something else to put it onto iTunes or something like that, okay? So if you try to convert that video on your laptop, it's probably going to take about 2.5 hours. You try to convert it on your laptop, it's probably going to take a little over 1 hour. You try to convert it on like a Mac Pro or one of the high-end Dell servers that has, you know, like 12 cores, it might take like 5 minutes. Because those are problems that you can divide up amongst those different cores. That's where that performance starts making a difference. Not in how we use our computers 98% of the time. That make sense? Okay, so kind of spinning this back to where we were going with this, performance isn't always our concern. It's only sometimes our concern. So a loosely typed language is not necessarily worse. If you were writing a video game that was very reliant on performance, you probably would not choose a loosely typed language. You would choose a strongly typed language because by allowing the programmer to explicitly say what kind of values can be stored in variables, you're taking a level of oversight away from the computer. It does not have to check a variable before it uses the variable because the programmer's told it what kind of values go in there. Famous loosely typed languages are stupid languages like VB.
Thanks a lot.
I worked for a company in Chicago doing VB programming for a while. Nothing wrong with VB. But you can relate to this. In VB, there's about 3 different ways you can even define a variable. It doesn't matter what you put in a variable. Even if you define a variable, in VB, you can define a variable with a type or without a type. You choose. So it's like neither loosely typed or strongly typed. It's just whatever. The other thing about VB, which is funny, is you could put an integer into a variable, do math with it. Then you could put an ice cream cone into that same variable, do math with it, and it will work. What does it mean to add 6 to an ice cream cone? VB will pump out an answer. Okay? It won't make any sense. But it will not yell at you. It'll say ice cream cone plus 6. That's a hot dog. Here. It's just a dumb language. But a lot of stuff was written in VB. VB was originally designed by Microsoft as being a rapid application development environment, RAD. The idea was you didn't have to be, again, talking about performance, business applications typically need to be functional, not high performance. They're not like a video game. You didn't have to be a great programmer to put together something functional using Visual Basic. Visual Basic was meant to allow non-programmers, or relatively non-programmers, to write relatively robust business applications. So you had this army of people writing business applications who were not programmers using Visual Basic. Now, this would have been okay had Visual Basic been a little bit more stringent about the rules. The problem with Visual Basic is it let you get away with everything. So in many ways, old Visual Basic programs are actually hard to maintain because they let the programmers basically get away with murder. Okay, so strongly typed versus loosely typed languages. One's not necessarily better than the other, but what should come to mind is if a language is strongly typed, think about performance. If a language is loosely typed, think about less performance, I guess is maybe the easiest way to put it right now. Java, C#, Objective-C, C, C++, all those are strongly typed languages. Two types of programming languages. We have interpreted and we have compiled. This slide deals with the difference between languages from the perspective of how the programs written in these languages are executed. Interpreted languages are executed in real time at runtime. A compiled language is executed based on previously interpreted code prior to runtime. So to kind of put this in perspective, we're talking to a computer, but let's take this to human languages first. Okay, so So you're from Saudi Arabia. So what's the native language?
Arabic.
Arabic.
Saudi Arabia.
Okay, I don't speak that. Okay, so let's say that you did not speak English, and I need to be able to communicate with you. So I speak English, you speak Arabic. We can't talk to each other directly, right? Huh? I need an interpreter. Anybody else in here speak Arabic? All right, we got this. Who speaks better Arabic?
I don't know.
All right. I'm gonna go with him because I don't trust this guy. Okay, so anyway, so he's gonna. But you also speak English. Anyway, so he speaks English and Arabic. I speak just English. You speak just Arabic. So in order for me to talk to you, I need to talk to him, and in real time, he's gonna interpret what I'm saying and convert it into Arabic for you. Okay, that's an interpreted language. With an interpreter, I can then communicate with you, right? But it's slow.
Sure.
Right? Because of this middleman.
Mm-hmm.
Okay? So interpreted languages work that way. It's happening in real time. I am speaking English at the same time as you are understanding Arabic. So I'm speaking Scheme or PHP or something like that, some programming language, at the same time as the computer understands zeros and ones. Okay? But at the exact same time, at runtime, while the program is actually running, we have an interpreter. We have a dude like him who's listening to whatever language I'm spitting out and converting it in real time to the language the computer understands. Okay? Nothing wrong with it, but certainly doesn't scream high performance. Make sense? A compiled language will work this way. Let's say I have a long thought that I want to convey to you. So rather than it being this back and forth conversation thing, I'm going to sit down and I'm going to dictate to him. I'm going to say, this is what I'd like you to say to him in Arabic. And I dictate the whole thing. He writes it all down. So he listens to my English, writes all the Arabic down. So he can hand you a piece of paper and you can just read it. So maybe I said just as much as I said to you in this real-time conversation, but in this case, he's pre-writing it. He's pre-interpreting it. So when you get the message has already been interpreted into Arabic and you're just going to read it natively.
So the interpreted one is faster than...
Other way around. The interpreted one is when I'm using an interpreter. The compiled one is when I get all my thoughts out there, give it to the interpreter, who then converts it way before he has to talk to you. So maybe he converted it a week ago for me. Kind of like, you get a book, and a book gets translated into another language. It's not like that's translating in real time. Somebody got the Bible and translated the Bible into 30 different languages, and then you go and buy it, and now that's the deal. Okay, so that's how a compiled language would work. The work was done up front so that it's real time while it's being executed. Okay? So interpreted should scream slow. Compiled should scream fast. In an interpreted situation, you are receiving my message slowly because it has to go through him in real time. In a compiled language, you are receiving my message quickly because it went through him a while ago. His time was not your time. Okay? You're just benefiting from it. So now to kind of tie the knots here, compiling. We have this term called compiling. Compiling translates
Because it goes down a level each
from
time.
high level to low level. And remember, high level had a one-to-many relationship with the CPU. Low level had a one-to-one relationship with the CPU. And when you execute a low-level language, it gets mapped to magic tricks on the CPU. So there's two levels of translation. So for those, if you've been in the industry, you've probably heard two different terms before. Compile
Compress.
and linking.
Oh.
Ever heard the linking before? Compiling and linking. Ultimately, what you produce is a set of assembly language instructions, a set of low-level language instructions that we can feed to the CPU, and the CPU interprets them based on its list of mapped functions, mapped magic tricks, as I refer to them. Compiling and linking is kind of a two-step process, because often you have a program, like you mentioned with your web program, that has JavaScript, a JavaScript library you bring in. You're going to compile a high-level program language down to a low-level language, but at the same time, you need to link in any extra libraries. So what you're left with is a pile of low-level language, collection of low-level language. That is a type of food that a processor eats.
Gotcha.
Okay? Processors eat instructions from a low-level language and react to those instructions by performing the magic trick that each of those maps to. Does that make sense? So the thing that we should really think about at this level, notice that the pattern that's emerging here over the last couple of things we've talked about deals with performance. Interpreted languages tend to be lower performance. Compiled languages tend to be higher performance. You know, I can only speak to him so quickly if you're interpreting what I'm saying in real time. You've got to be able to keep up, right? It's not that we can't pull it off. It's that I can only babble so quickly. Let's say we're not, all three of us aren't in the same room. Compiled version is I write my email in English. I email it to him. He reads my email and says, okay, well, let me create the Arabic equivalent. Then you send that completely converted email to him, and he just reads it in Arabic. That's the compiled version. So it's not a real-time thing. You know, you converted my words completely separate to him experiencing my words. So you might have done it on Tuesday, and 6 months later, he actually executes my words by reading them. But he's reading them in the language that he understands, not in the language I originally delivered it in. I delivered it in Java. He's reading it in assembly language, if he's a computer. Most languages we'll deal with will be high-level languages. Okay? Low-level languages don't fit into categories of loosely typed or strongly typed or anything like that. Low-level languages exist to be eaten by CPUs. Okay? That's the only reason low-level languages even exist, is so the CPU can eat them, because they have that one-to-one relationship. All right? Now, functional languages tend to always be interpreted. Procedural languages often are compiled but may be interpreted. Object-oriented languages often are compiled but may be interpreted. A good example of it's almost a hybrid between a procedural and object-oriented language. A good example of a modern-day, high-level, procedural / object-oriented language that is interpreted is PHP. Okay, PHP is an interpreted language. JavaScript, also an interpreted language. Who interprets JavaScript? There's a piece of software, an interpreter that lives inside your web browser. That's who interprets it. So when you get total geekdom and you like programming, or at somebody's house and you need to solve a problem, and the correct tool for solving it is writing a program to solve it, yet you don't have any computer stuff laying around, as long as they have a web browser, you can write a program. Open up Notepad, write it in JavaScript, run it in the web browser, you got your answer. Now, general purpose languages are almost always high level. In fact, I would say are always high level, are always procedural or object oriented. Oh, well, no. They can be any of the three. And can be compiled or interpreted. I don't think that makes a real strong case there. Interpreted languages are almost always loosely typed. Compiled languages are almost always strongly typed. I think that tends to be a truth. So I guess I connected some dots.